My name's David Dewitt. My co-author is Rima Nemi. If any of you are SQL Pass people, I had no idea she was coming today. Otherwise, I would have had Rima give this talk. But anyways, I'm glad to have Rima here. Oh, good. Clicker not working. This is... Yes, you told me. We tried... No. Okay. What is going on here? Which one? No, that. Oh, not touch.
There, yeah, just go there, or key should go.
Let's see if this is going to work. No, it's not displaying.
That is 8, right?
Yep. This was working.
You have 7. There's another one, 7. Maybe we swap this.
We got some help. Let's try one more time. Okay, here we go. Let's see if this is going to work. Okay, great. Thank you. Thank you, Lindsay. Okay, so who am I? My name is David Dewitt. I was a faculty member at University of Wisconsin-Madison for most of my career. Joined Microsoft in 2008. And I manage a small lab in Madison, Wisconsin, which reports into the SQL team. So what I'm going to do today I'm going to talk about Polybase. And for those of you that are aware of the name, it's a feature that we've delivered as part of the SQL Server PDW appliance since 2012. And as part of SQL 16, we're going to bring Polybase to the box product. So we'll talk a little bit about what it is, why it's interesting, how we build it, and what we might do next. So Polybase is aspirin. It relieves customers' big data pain. It's air because it allows customers to survive in the 21st century. And it's a jewel because we think we did it right, and we think customers are just simply going to love it. So the goal of Polybase is to provide a bridge between the relational world that you're all familiar with and the big data world of Hadoop. So it brings scalable T-SQL, standard T-SQL query processing for combining data in both universes. And this is really important to understand. We're not intending this to be a Cloudera or a Hortonworks compete. We're really interested in combining relational data with Hadoop data. So more specifically, from SQL 16, you'll be able to connect up to either Azure storage or Hadoop storage and run T-SQL queries that combine data from both these environments. So why is there all this interest in big data? Well, first of all, we all know about the Internet of Things. There's a variety of data sources generating, whether they be tweets or machine sensors, your Nest thermostat. Somebody's probably mining my Nest thermostat right now at Google. Acceleration data, and I'll come back to one of the use cases. People have found data too valuable to delete, and they want to keep all the data that they ever accumulate. And it's all being driven by really dramatic decline in the cost of storage. If storage weren't just pennies per gigabyte at this point, we would not have a big data revolution. So the hardware has made big data possible. Now, I'm not going to go through this entire slide, but basically this is sort of a picture of the Hadoop ecosystem. And at the bottom of the Hadoop ecosystem is a distributed, scalable piece of file system called HDFS. And everything, as you'll see, surrounds HDFS. There's MapReduce, which is a distributed programming framework. There's Pig, there's Mahout, there's Hive. There are all these pieces that surround HDFS. And Polybase relies heavily on HDFS also. So here's the Hadoop world's view of things. There's the Earth circling HDFS, scalable distributed file system, underpinnings of the entire Hadoop system, as I tried to indicate on the previous slide. The really beautiful thing about HDFS, and it is really beautiful, is not only is it scalable, but it's highly fault tolerant. Companies like Yahoo will run HDFS on thousands of nodes, and it deals with block replication, all transparent to the applications sitting on top of it. Big data lands in HDFS, and it has become an intergalactic standard, as this cartoon illustrates. Everybody uses HDFS, okay? But the important thing to know, you're never going to go put your transactional data in HDFS because it's append only, okay? You can add data to it, but you can never update in place. Now, when MapReduce and Hadoop first came out, people used MapReduce, which is a programming paradigm, to write distributed applications on top of HDFS. And gradually, that's being replaced with various warehouse-like, SQL-like products, such as Hive, Hawk from Pivotal, Impala from Cloudera, and Spark and Shark from Databricks. All of these, in effect, are parallel SQL data warehousing products for HDFS. And those are what a lot of customers use to gain insight from their HDFS big data file sets. Polybase has, as I tried to allude to earlier, has a different worldview. We believe that customers are going to continue to maintain a lot of their data in standard relational database systems. And we want to build a system, we set out to build a system that would allow customers to maintain their investment in BI tools and T-SQL application programs, but extend the reach of SQL Server to encompass HDFS. And so that's the difference, and that's really an important difference. We're not building a parallel data warehousing product just to process data in HDFS. We very much want to enable our customers to query their standard relational transactional data, their relational data warehouses, and also extend that universe off to HDFS so they can query that with a single application. As I said earlier, we first brought out Polybase as part of the SQL Server PDW v2 release in 2013. And I'm going to talk a little bit about the use cases. People use it as an ETL tool. They'll dump their data into HDFS, they'll clean it up, maybe using MapReduce, and then they'll load it into the parallel data warehouse PDW. Other people use it as cold but queryable storage, and I'll give an example of that in a second. People will stick their social data from Twitter into HDFS and then use Polybase to mine those tweets. And finally, some people are using it to dump sensors into HDFS and then do analytics on top of that. So those are for examples. Let me start with Progressive Insurance, who's one of our PDW customers. Progressive, if you're a good driver, is probably a great insurance company to go with because they'll take sensor data out of your car, so they're doing telemetry data out of your car. They'll combine it with your customer information, and they'll generate a price policy that rewards good drivers. I do not have Progressive Insurance. And I'm sure my old boss, Quentin Clark, who drove a Ferrari, wouldn't have Progressive Insurance either. So another example with a slightly different use case is Shinshi-ga, and I'm sure which is Korea's Amazon. They take tweets, social media data, which they dump into Hadoop. They take their structured product data, and they do basket analysis combining these two different worlds of data. So again, non-relational data put into Hadoop, relational data on their products in a standard PDW SQL Server data warehouse, and then they combine these two using Polybase. Now, the beautiful thing about Polybase is because it provides a T-SQL interface to Hadoop data, is all the standard BI tools work, whether it's Excel, Power View, Tableau, all those tools continue to work over non-traditional data, over queries that combine relational data with HDFS data. An example of sensor data comes from an oil and gas company, which I cannot name. They take their rig data that they get from their rigs, and they put cold data off in Hadoop, and they put hot data, the most recent data coming off their rigs, and they stick that in PDW, SQL Server PDW. And then they do predictive analysis. Here's how these rigs behaved in the past. Here's how they're behaving now. Can we predict failures? So there are three examples. Progressive, which is doing sensor data. Xinxi, which is doing social media data. And then the oil and gas company, which is also, I guess, doing sensor data in a slightly different way, but using HDFS as cold but queryable storage. So the Polybase project started at my lab in Madison, I don't know, in 2011 or 2012. Actually, Rima's original idea. We first released it in 2013, and there have been a series of improvements. And as Ranga announced in the keynote, or it was announced in the keynote earlier this week, I guess yesterday, we're going to release this as part of SQL 16. And who knows what we'll do with it in the next couple of years. So what is Polybase? Polybase is a querying capability over relational data and HDFS data. Why? Because customers want to be able to analyze big data along with the relational data. And now I'm going to talk a little bit, I'm going to focus a lot on how we actually built this. So to talk about that, I want to step back and talk about what the components are in PDW. So this is definitely not vaporware, okay? That's the one thing I want to say. Definitely something that's been working as part of PDW, and we're going to reuse almost all the components of Polybase that we built for PDW in SQL 16, and that's what I'm going to do in this part of the talk. I'm an engineer. If you didn't want an engineering talk, you shouldn't have come into this room, okay? So here we have a picture of SQL Server PDW boiled down into one orange box. It's actually an appliance. It's got multiple nodes. I'll drill into that in a second. And we took SQL Server PDW and we built this layer, this extension to it called Polybase that allows the SQL Server PDW customers to query both the relational data in the appliance and HDFS. Standard T-SQL interface to the data, no need to write MapReduce jobs. Nobody wants to write MapReduce jobs, which is why all our competitors are building SQL-like database systems. They unfortunately don't know anything about query optimizers yet, so they have a way to go. We leverage PDW as a parallel database appliance. We leverage the PDW query processing mechanisms to process HDFS data in parallel. Unlike Scoop, which you may be familiar with, these slides are on my website. Don't take pictures. GraySystemsLab.com, search down to people. The slides are all there. There's no copyright. Okay, I'll give you another link. Please don't waste your time. I'm an academic by training, so anything I produce is basically in the public domain. There's this other mechanism that people sometimes use to connect their relational database system to Hadoop, and that's called Scoop. Really interesting piece of software that doesn't work very well. One of the key design objectives we had in building Polybase or PDW is we want to move the data in parallel between the parallel compute environment of Hadoop and the parallel environment of PDW. And I'll talk a little bit about that today. And finally, we wanted, when we set out to do the project, we wanted to use the SQL Server or the PDW Query Optimizer to figure out what computation should be moved into the Hadoop cluster by running MapReduce jobs, because we automatically generate MapReduce jobs out of SQL predicates. All these components are now part of SQL 16, including the ability to run SQL 16 as a cluster of compute clusters to compute against HDFS resident data. So we're bringing not just big data capabilities to SQL Server, but we're bringing big data capabilities to SQL Server in a scale-out manner. So I'm going to, now to show you how we build it, I'm going to show you the pieces that we added to PDW. And I'm going to talk a little bit about PDW. So PDW is sold as an appliance currently, coming as part of SQL DW or Azure Data Warehousing, whatever it's currently called. It's built with a number of compute nodes, each of which has a SQL Server box. So you can think of these as VMs running on a different hardware node. And then it has a control node also with a SQL Server instance. Clients connect into it using the standard JDBC, ODBC, et cetera. And they connect into a process called the PDW engine service. And I'm going to get more into that. And this takes and parses the SQL, does validation, authorization, produces a parallel query plan, controls the execution of the parallel query plan on those compute nodes, and then returns the results. So the engine service is sort of the contact point for an application or a query. The second major component of PDW that's outside of SQL Server is something we call the data movement service. So it's another process that is used to shuffle data between the compute nodes, between those SQL Server instances running on the compute nodes, and each other doing various parallel queries that are coordinated by the engine service. So it's a separate process, and there are some parallel queries that do require shuffling, true of any parallel database system. So highly scalable SQL Server data warehousing offering, one control node that has its engine service and DMS, and multiple compute nodes. So that's the key thing you need to remember for now. And the fact we reuse those. So let's look into what a typical Polybase setup looks like today when you buy an appliance and decide to use Polybase. You have this appliance in some form factor, quarter rack, half rack, multiple racks. It has the SQL Server instances on it, on each of the compute nodes. The database gets partitioned among those disks I've shown there. So every table is partitioned among all the disk drives to give high performance. And then there's a Hadoop cluster of some flavor. Generally in-premise, but it can be in Azure. It can be a Windows Hadoop cluster. It can be a Linux Hadoop cluster. It can be a Hortonworks or Cloudera distribution. So we've tried to be very open about what kind of Hadoop clusters and distributions we expect, and we live with the Linux world. And it supports many of the popular HDFS file formats, text, RC, ORC currently, and then Parquet, which is Cloudera's HDFS file format. And I'm not going to go into those, but we've tried to be totally open on file formats. We don't have a Microsoft proprietary file format here. Now, in building Polybase for the appliance, there were 4 key challenges. How are we going to support all these arbitrary file formats, which are open sourced and accessed typically in Java? We wanted to parallelize the transfer. No single bottleneck was acceptable. We wanted to impose some structure on this unstructured, quote-unquote, unstructured data. There's no really such thing as unstructured data except free text. So every piece of data has some structure to it. Otherwise, it's pretty hard to crack except doing text search. And then we wanted to exploit the computational resources because we accepted the fact that it could be a small 4-node PDW appliance and a 30-node Hadoop cluster. And if we're running a query that uses a lot of Hadoop data or processes a lot of data, we wanted to be able to push computation to that Hadoop cluster to take advantage of those computational resources. And I'll come back and talk about that. So that's this last bullet. So recall earlier I said that every compute node and the engine service, in addition to the SQL Server instance running on that node, also has its external process, the data movement service process in orange, that is used to shuffle data. Well, to build Polybase, we took this process and added a Java component that we call the HDFS bridge. And what this does is, to the PDW software and now to the SQL 16 software, it hides the complexity of HDFS. And this uses standard record readers and record writers so that we can access any kind of HDFS file format, text, RC, ORC, and then coming in Parquet. This DMS process is also used to transfer things in parallel. So, and I'm not going to talk about how we actually do this, but if you actually look at how a PDW appliance operates or how a SQL 16 setup will work, each of those DMS processes, when we're processing data out of HDFS, will talk directly to the data node to get its split of data. So there's no single bottleneck. We'll scale with the limitation of, if the ideal situation is there are an equal number of nodes, but we'll scale to maximize the data we can transfer in parallel. Obviously, if you put a 1 megabit link between a big Hadoop cluster and a PDW appliance, not going to work very well. So the faster the link that connects those two compute clusters together, the Hadoop cluster and the PDW appliance, the faster the transfers will happen. But they will always happen in parallel. Now, how do we impose structure on this semi-structured data? So the thing that you do, and I'll try to demo this later, except for my technical glitch, which may not get to, the first thing you do when you set up a Polybase installation is create an external data source. And this thing will identify the IP address of the name node, that's the location, and the job tracker. And the job tracker is the Hadoop component to which you submit MapReduce jobs. So you do that once per Hadoop cluster. And the DBA does it once, never has to do it again. The second thing the DBA must do in setting up a Hadoop or a Polybase installation, whether again on the appliance or SQL 16, is to define an external file format. So here I've done a text file format. Data compression is JIP codec. Field terminated is /t. And it's, again, we have standard ones, 3 lines to do RC or ORC, once per file format. And the final step is to create the external table. So here I've created a table customer. It's basically a relational view on top of that HDFS file. I will indicate the HDFS file path, which could be to an individual file or a directory of files in HDFS. I'll say what format the file is in, and then I'll also say what cluster it's on, because you can have multiple Hadoop clusters. You don't have to just have a single Hadoop cluster. So here's a simple example. I have some customer table in HDFS. I'll select star from customer, where some predicate, and here's a possible execution plan. I'll create a temporary table on the Hadoop, on the compute nodes of the appliance. I will suck all the data in from HDFS into those temporary tables in parallel, and then I'll run the selection. This is always a viable path. It's basically a temporary load of the data into the appliance from Hadoop, and then do the residual processing in Hadoop. Now, this is fine, but doesn't take advantage of the computational resources that Hadoop cluster offers. So this is what I want to talk about at the end. So here's what actually happens under the covers when a SQL query comes in. It comes into that control node to the engine service process. It gets parsed, and the parser rips out all references to those external tables sitting in HDFS on the Hadoop cluster. We do parallel query optimization to figure a cost-effective plan using, and we have statistics on the HDFS files. We do a plan generator, and that will include generating MapReduce jobs on the fly to run on the compute cluster. And then once the parallel query plan has been produced, the engine service will schedule, by sending these MapReduce jobs to the job tracker on which the data resides, a MapReduce job to push the computation down. And there it's shown running on the Hadoop cluster. So here's the big takeaway. SQL query comes in to either PDW or SQL 16. We make a cost-based decision based on the size of the HDFS file, the column level stats that we have on that HDFS file, and we make a decision exactly how much computation to push to the Hadoop cluster. We'll push that as a map job. The MapReduce job the Hadoop will run that. It'll produce, iterating back and forth, maybe a sequence of MapReduce jobs. Finally, that's finished. We pull the results from that computation into PDW or SQL 16, and we shove it out the top to the user. So this all happens totally under the covers. It's just to the user, it just looks like T-SQL. All this magic happens underneath. And again, what we're bringing to SQL 16 are exactly these same components. Yes, there was some new code to get this into SQL Server as opposed to a bunch of separate processes, but all the basic code is carried over from SQL PDW to Azure DW running in the cloud to SQL 16. So let me give another example of what happens. So here's a case where I'm going to push all the computation into the cluster. I've got the same customer table. I'm computing some average with some predicates, grouping by nation key. The query optimizer will generate this MapReduce job. And we're going to do both the filtering and the aggregation directly in HDFS. And we leave the output in a temporary file in HDFS. Then we'll create a temporary table on the compute nodes, suck the data out of HDFS, and return those results to the user and run the residual computation as a SQL step. So again, totally under the covers. Same thing will happen in SQL 16. Now, let me just wrap up and talk a little bit about what we're doing for Polybase. So first of all, we've tried to make this simple, okay? Query data in Hadoop and or PDW via standard T-SQL. Highest possible performance, okay? Parallelize the transfers between the PDW appliance and the Hadoop clusters. Push down of SQL operations to Hadoop to take advantage of those computational resources. Open. Nothing proprietary this. Linux, Windows, Hadoop distributions, Cloudera, or Hortonworks distributions. No MapR at this point if you're a MapR fan. Full integration with Microsoft Office and BI tools, including third-party tools such as Tableau. The pieces that we're carrying forward to SQL 16 include the engine service, which is used to parse, which is used to produce a parallel query plan over both relational data and HDFS. The data movement service that's used to shuffle data among the compute nodes of the appliance, as well as to move data in parallel between the compute nodes of the PDW appliance and HDFS. The bridge component, which is part of DMS, which is how we use to talk to the different Hadoop file formats, or Azure in case of Azure. The external table construct, which is how we impose some structure on top of the data in HDFS. And finally, MapReduce pushdown, which allows us to take advantage of the computational power that sits there in the Hadoop cluster. So again, all these components have been shipping as part of the PDW appliance for the last 2.5 years, okay? And they will all have all been repurposed to sit inside SQL 16. So Polybase for SQL 16, what does it mean? Well, in addition to this ability to process data in HDFS, it will all, with SQL 16, you'll be able to stand up clusters, and I'll illustrate that, of SQL 16 instances. This will be done, and I'll talk about how we do that. This will be absolutely trivial for the customer to stand up. Basically, during the install process, you'll get a chance to form a cluster. So this is for the first time we're bringing to the standard box product of SQL Server the ability to run computations in parallel. So as opposed to a single process instance, single server instance. As has been with Polybase in the beginning, T-SQL to query both data and relational data and data in HDFS or Azure. All standard BI tools and full T-SQL interface. One caveat, which I'll get to later. So here's the process to set this thing up. First of all, you got to have a Hadoop cluster. We're not going to automatically deploy Hadoop clusters for you. We're going to assume that anybody who wants to use this capability will have the knowledge to set up their own Hadoop cluster. Okay, we're not going to try to automate that. We're not going to try to tell you which brand to get. And you can have a small Hadoop cluster that's only 1 or 2 nodes or virtualized on a big server. But here I've drawn, there's a name node, which is a standard component of the Hadoop cluster, and there are a bunch of data nodes, and Hadoop automatically manages these in terms of fault tolerance. So that's step 1, and we're going to assume that customers do that themselves. Again, HTTP 2.0 or above. We're not backward supporting 1.9, 1.8 releases. We're going to insist that you move forward. Linux or Windows, though we suspect 99% of the customers will probably set up Hadoop on Linux. And it can be on-prem or in Azure. So if you want to run SQL 16 and IIS VM, talking to Cloudera in Azure, that's fine. Or it can be Azure Storage also. Step 2 is to install SQL Server. Okay, so we're again not trying to, at this point, automatically deploy SQL Server on a whole bunch of boxes automatically. And we did a presentation to some of our customers in November, and we asked them whether an automatic deployment across large numbers of nodes was something they wanted, and they uniformly said they did not want us to get into this process, okay, or this mechanism. They wanted to deploy SQL Server using the same tools that they're currently using to deploy SQL Server. So to use Polybase, you'll just have to install SQL Server. And when you use the SQL Server installer, you'll be asked whether or not you want to use the Polybase feature. Okay, so there'll be a little checkbox on the installer, and you'll check that checkbox. And if you check that checkbox, the installer will lay down on disk some DLLs. And it's going to, remember those engine service and DMS processes I talked about as part of PW? Those DLLs are going to get installed on the disk drive. Now, this may change. It's probably going to be the case that by the time this reaches RTM, those processes will actually be inside SQL Server. And I'll come back to that at the end. It's going to install them and register them as Windows services. So now you're left with a bunch of boxes, those light blue things, with some SQL Server bits running. And the next step is to turn one of those instances, which I believe will have to be an enterprise license instance, but I'm not a sales or marketing guy, so I don't know what the final decision has been made, into something we called a head node. So think of the head node as sort of analogous to that control node in the PDW appliance. So it's the point to which queries are going to be submitted. So one of the instances has to be labeled as a head node. And when an instance is turned into the head node, the engine service and DMS processes get started. Okay, so those are those external processes, basically unmodified from the appliance. Almost unmodified. The second thing you do is you turn 0 or more of these other machines into compute instances by starting the DMS service. And the first thing they do when they come up is they call home. There's some information in the registry. We're going to automate that a little bit later. But as part of CTP2, you'll have to do some manual work to make this work. But there's some information in the registry on these compute nodes that says where's their head node. And that's all that's really needed. Okay? So at this point, I have a head node and I have some compute nodes. And that's step 3. Now, one of the things that, and you saw this, if you went to the SQL DW keynote, you saw them cranking up the number of instances and cranking down the number of instances. One of the components they use to do that is something we built in my lab called flexible topology. And you can do the same thing in SQL 16. So eventually, you'll be able to turn compute nodes off dynamically, up and down, up and down. Time of day, maybe on the weekend, you turn them way up because you've got a big job to process. But if you got a big load, you can turn them all off, and you can have just a single instance. So we're going to allow you to dynamically adjust how many compute instances you're actually using at any one time. And this will be, again, SP configure, some kind of DDL. Now you do it manually. in the CTP2 bits. So here's what you have after step 3. You have a head node, and you have a bunch of these instances. And again, this is how it'll look in CTP, sort of look in CTP3 and RTM. The head node is the node, like the control node in the appliance, is the node to which queries are submitted. The compute nodes are used for scale-out query processing against HDFS resident data. We will do more down the road. I'll come back and talk about that. Now you're wondering, well, he talks about head nodes and he talks about compute nodes. If you have one SQL 16 instance, the head node is also a compute node. Okay, so you don't have to have 2 SQL Server instances. You can have one or more. Okay, so this head node is also a compute node, and it's always used as a compute node. If you have one head node and 3 other nodes, then you have 4 compute nodes. They're always used for doing computation. And again, to the extent we have time, we'll provide scripts and wizards to make configuring all this as simple as possible. But we're not going to take over the installation process of either the Hadoop cluster or the SQL Server instances. We're going to leave that to the DBAs. Now, there are some cases, I mean, if you go to Cloudera's website or Hortonworks' website, you can do single button installs, spread it over a big cluster. We just heard from the DBAs that we talked to and the customers we talked to, and that we're going to leave the SQL installation to you. So at this point, you've got some compute nodes, you've got a head node, and step 4 is to attach a Hadoop cluster. So remember before I said how we do this structuring? Well, so you create an external data source using a command like this, and if I have time, I'll do a quick demo. And you attach with one SQL statement, DDL statement. Here's my external data source. And you give it a cluster name and the type of distribution, and all of a sudden you've got your SQL 16 off pointing to this Hadoop cluster. You can have more than one, okay? We don't really care how many you have. For now, unfortunately, they all have to be the same brand, okay? And this has to do with the fact that we use Java jars inside the engine service. You can't have 2 JVMs running inside the engine service because the Hortonworks one is different than the Cloudera one. Blame those guys. Don't blame me, okay? Not my fault. Maybe we will fix it down the road. But for now, we sort of assumed, okay, most customers are going to pick a vendor, whether it be Hortonworks or Cloudera, and their Hadoop clusters will be all of the same variety. Those Hadoop clusters can be in Azure, okay? So in some ways, this is similar to StretchDB, except your external tables are explicit. They're not a partition of a single table. So that can be up there in Azure as a Hadoop cluster, Cloudera running in IIS in Azure, or it can be just Azure storage. That will be fine too. Okay, and within the Azure storage volumes, we support text, RC, and ORC standard Hadoop file formats. Now I've got the thing really set up, and again, I'm going to do this exactly once. Okay, I've got my SQL Server 16 instances as a cluster. I've got my Hadoop cluster, and I'm ready to start running queries. Okay, so T-SQL queries get submitted just to the head node. Okay, so this is really important to understand. We are not at this point providing the ability to have a PDW software stack on-prem. So let's just be really clear about that. I'll try to get that across. So T-SQL queries come into the head node. Those queries can reference data only on the disk or the database attached. The database is attached to that head node instance. Or data stored off in the Hadoop cluster as external data. The compute nodes are used for scale-out query processing against HDFS data or data in Azure. And I'll show you an example of another kind of scale-out query processing we'll be bringing in CTP3 or RTM. Tables on these 3 compute nodes in this example cannot be referenced by queries coming into the head node. So those are SQL 16 instances that are used generally for other purposes if that's how you desire to set it up. Okay, so this is not providing a parallel database system, a total parallel database system for SQL Server. It's providing scale-out query processing for big data stored in HDFS or Azure. It's an important distinction, and I hope that's clear. As I said earlier, the number of nodes can be adjusted dynamically. And the Hadoop clusters, in case you're wondering, in case I want to have one Polybase SQL 16 cluster here and another there, they can share the same Hadoop cluster, okay? So you can have multiple SQL 16 clusters set up, all sharing the same big data repository. Now, I've tried to get across this example again. So here I have this little table. I have 4 columns: scale-out storage, scale-out query processing, language surface, and delivery vehicle. And again, these slides are on graysystemslab.com in a couple different places. Under the Polybase link or under people and then Dewitt, you can find these slides. So SQL PDW provides scale-out storage for relational tables, for HDFS, and for Azure. SQL DW does essentially the same thing. Okay, you can have it happens to use Azure Storage for holding its relational tables, but there's a notion of a relational table partitioned across a number of storage volumes. SQL 16, the scale-out storage, in addition to the local tables that are on the head node, the scale-out storage is mainly HDFS and Azure. So there's a real critical difference there. And this is more of a business decision than a technical decision. Okay? Scale-out query processing. All of them can apply multiple compute nodes to processing big queries in parallel, whether against tables that are stored relationally or HDFS or in Azure. Same for SQL DW, standard parallel data warehousing product delivered in Azure. Scale-out query processing for SQL 16 is HDFS only. It'll be relational, HDFS, and Azure, and I'll illustrate that in the next couple of slides at RTM. Those first 2 products have a slightly limited SQL dialect they support. For SQL 16, we essentially have the full T-SQL dialect because it's architected slightly differently. PDW delivered as an appliance, SQL DW delivered as a PaaS offering in Azure, and SQL 16, you can run an IaaS, or you can run it as a standard box product on-prem. So again, you might consult the slides if you're a little bit confused, or you can send me an email and be glad to help out. Here are some limitations. So the CTP2 bits are basically done. And here are the limitations. So each SQL 16 instance can only participate in a single Polybase cluster. So if you have 4 SQL 16 instances that you've installed, you can have one 4-node Polybase cluster. You can have 2 nodes or a 3-node and a 1-node, but you can't have them overlap. And this has to do with the way the DMS software is currently architected. We'll hopefully eliminate that by RTM. Oh, one thing I didn't say is we're going to assume that you're using Active Directory, okay, strictly for security purposes. Okay, so if you don't like Active Directory, talk to us. For CTP2, which is the May-June available, we're going to call this multiple compute nodes not production ready. Now, what does that mean? That means it works, but we haven't tested it. Okay, use at your own risk. We will provide you a scripting mechanism to help you set it up. It will probably be, you'll have to just enter a few things. It's actually it's pretty trivial, just changing some registry entries. But we will not have tested this by the CTP2 release. No support for varchar max or unique column types. I don't want to explain that. There are some, because we're reusing those PDW components, especially the data movement service, this number 3 is a carryover from the fact that we reuse that software without rebuilding it, okay? Because again, we're trying to be lean and mean, and so this is a limitation of PDW, it's a limitation of SQL DW for now, and it's a limitation of SQL 16 for now. Maybe we'll get it fixed by CTP3 or RTM. No, this weird sentence, no join, no scale out for joins between tables on the head nodes and external tables on HDFS, blah, 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 blah. What does that mean? Okay. So let me walk you through this example. So here I have a 4 compute node Polybase cluster on top, and there you see a customer table that's sitting on that head node. Down below, I have a 4 node Hadoop cluster. I just picked 4 to make the slides work, okay? Not because there's anything magic about 4 versus 4, okay? And it looks pretty. So orders is an external table sitting down there on the Hadoop cluster. Customers is sitting on the head node. The query is a join. It gives me orders whose price is greater than 1,000 and joins orders with customers to get the customer names because I want to send them some promotional literature. Okay, so this is standard T-SQL. The user has no clue they're touching external tables. Now, in CTP2, this is what will happen. We'll run a MapReduce job to filter out all those orders which are less than 1,000. I want to only find the orders greater than $1,000. So you notice if you look at my fancy animation here, I ran the MapReduce job, and those orders go from, you're supposed to ooh and ah, from blue to yellow, okay? So the output of the MapReduce job is a HDFS file called temp. It's broken into a bunch of pieces on this HDFS cluster. Again, all this happens under the covers. The second thing that happens is the software is going to pull that temporary table of orders greater than 1,000 into the head node and land it in a temporary table in SQL Server on the head node. And then it's going to do the join between customers and that temporary table using just the head node. Now, if there are not many orders greater than 1,000, this might not be too bad. But if there are a whole pile of orders greater than 1,000, this performance is going to be not too good. CTP2, okay? So please, if you take CTP2 bits, don't blog and complain about this. I warned you, okay? Now, what are we going to do by CTP3 or RTM? Much better scenario. Select same query, customer on the head node, orders down there in the Hadoop cluster. We're going to run a MapReduce job. We're going to push that predicate down into the Hadoop cluster to filter out anything less than or equal to 1,000. That'll land in a table on HDFS. Then we're going to, remember this DMS software loves to read from Hadoop in parallel. So the next part of the plan will be import the result into those SQL instances on the compute nodes, okay, in parallel. And we got an equal number of blocks from each of those, from that HDFS file, now sitting in temporary storage. We actually will probably stream it, but I just want to illustrate this. Then, watch this next animation. I'm going to take customer. If there are predicates on customer, like they live in Chicago, I'll apply that. But I'm going to take this customer table sitting on the head node, and I'm going to redistribute that customer table to all the compute nodes. So 1/4 of it's going to stay on the head node. Another second quarter is going to go on the second instance of SQL 16. The third will go on the third. The fourth will go on the fourth. If there are 50 of them, I'll spread that customer table across all 50 of those nodes on the fly, and then I'll do the join. So this is what I mean. I don't have scale-out storage for customer, but I have scale-out query processing for customer in RTM or CTP3. And it turns out it's not a hard technical issue. There's some hard transactional issues associated with this work. And Rima and some others in the lab have been working on a design document. Redistributing the data is trivially. We know how to do that in PDW. We take data off the head node, the control node, and redistribute it. It's the transactional issues that are tough. And so this is what the key difference between CTP2 and CTP3 is, this ability to redistribute local tables. Now you might say, what if customer and orders were both on the head node? Forget this external data HDFS junk. If customers and orders are both on the head node, and we think it's cost effective to pay the network cost to redistribute them. Again, all this will be done using query optimization. We will take 2 tables on the head node and redistribute it among the compute nodes and run the join in parallel. But again, it's not scale out relational storage, it's scale out relational query processing. And there's a fine line, and I hope that's a little bit clear. Some questions you might have asked, or you might want to ask, and I think I'll have time after I do demo. Will always on Hadron be supported? Absolutely, even with CTP2. Can a compute node be used for other workloads? Yes, that's what we expect will be the norm, but that'll be up to the customer, okay? So if a customer wants to set this up to use those compute nodes for just scale-out query processing on Hadoop, fine, I don't really care. But our expectation is they will be used to run normal SQL workloads. And again, this will be under the control of the DBA, what happens. We love this one. Can a compute node share a machine with a Hadoop data node? Yeah, performance is fantastic when that happens. But that requires that you running Windows Hadoop. And not many people, unfortunately, run Windows Hadoop, okay? Because we can't run SQL Server on Linux. So if you have a Hadoop cluster that's running Windows, and you put so you have your data nodes, and you have your name node, and you have your job tractor on this Hadoop cluster running Windows, and you put your compute nodes there, the system is fantastically fast because there's no network traffic. Everything happens locally. I mean, there's networking trafficking when you're shuffle. But yes, the answer is yes. We wish more people would set things up this way. Probably not going to happen. This is a decision that has not been made, to the best of my knowledge. Don't hold me accountable. Lindsay's here somewhere. Where's Lindsay? Did Lindsay leave? Oh, okay, fine. Lindsay's not here. Okay. My understanding is one enterprise license for the head node. The other nodes can be standard. Don't hold me to that. Unfortunately, MapR, no plans at the present time to support MapR. We're always interested in this feedback as whether this is something we should be doing. Is there a limitation on the number of compute nodes? No. Why is it not possible to have my SQL 16 compute cluster talking both to a Hortonworks distribution and a Cloudera distribution? This has to do with this Java issue. And if they ever got aligned on the same jars, then we'd be able to do this. But you can't only run one JVM inside that engine service process, and we don't want to unload and reload. So this is, unfortunately, not something that we're going to get fixed, probably by RTM. Now, what are we going to do next? And I don't know when CTP3 is, okay? I don't know whether it's October, November, December. I talked about this local table scale-out query processing. We will definitely have that done. Quote-unquote official support for compute nodes. This means an official script, maybe DDL to turn those compute nodes on and off, but tested, okay? So we will have it thoroughly tested. Enhanced performance mechanisms. These are like, I'm not the dev manager for this project or the dev lead, or I'm just this guy off in Madison with most of the great talent that I have, with a lot of the great talent I have. Here are the things that we'll probably do to enhance performance by CTP3 and by RTM. We're going to pull those engine service and DMS inside SQL Server, so we don't have 3 processes. This makes failover much easier because instead of SQL Server failing over, well, what happens to the engine service when it fails over? So by pulling those in, we'll not only get much better performance, but we'll also get cleaner failover. And we think the performance improvements will be dramatic. Might not make CTP3, might be RTM. We've started this work. One of the things that is coming to the appliance, and will come to SQL 16, is streaming data. Some of the examples I showed you showed data coming out of HDFS landing in SQL Server temp tables. We have some software built that will stream data out of HDFS, never landed on disk, directly into the bottom of a SQL query plan without first landing in temp table. Dramatic performance improvement. This will undoubtedly, when we pull the DMS, well, this capability will come no matter what we end up doing. So we'll get big performance gains. No more Java, okay? Microsoft's not a big fan of Java. Don't quote me on that. We've built in my lab native libraries for talking text, ORC, and Parquet will come. We will not probably do native libraries for RC because everybody has switched from RC to ORC, which is, by the way, and I should have mentioned this earlier, I apologize. ORC is the Hortonworks preferred HDFS file format. Parquet is the Cloudera preferred HDFS file format. These are the two main ones to support. And we're currently doing RC and ORC in the appliance, and we'll bring Parquet forward going forward. But we've seen in the lab 2x performance improvement by getting Java out of the picture, in addition to increased stability. Finally, something that is really near, oh, you're not supposed to do that. I'm going backwards, sorry. Okay, sorry. The last bullet, indexing HDFS data. This is also something that we have working as a prototype. Mostly you can process an HDFS file by reading it from the beginning to the end. Now, Hadoop and Polybase, they do this in parallel to get great scan performance. But if you want to do small range queries or single row lookups, customer equal 3333, you're going to scan the entire HDFS file. And we've actually extended the SQL Server and PDW indexing mechanisms so that you can actually index data in HDFS. And again, there's like, this is at the bottom because I got to still twist some arms to get this in a shipping version. But it'll allow you to run basically point queries against HDFS and get back, in sub-second response time. Wrapping up, simplicity. Query the data in Hadoop, Azure, SQL Server, all using standard T-SQL. Transfer data in parallel. You have a Hadoop cluster consisting of some number of nodes, a PDW cluster, or a set of SQL 16 instances set up as a Polybase cluster. You don't want to transfer the data through, you don't want that transfer of data to have a bottleneck at any point. And that's why we use this DMS process. We use the HDFS bridge. We transfer data directly from the DMS process, running on each of those SQL 16 compute instances to the Hadoop data nodes, fully parallelized, no single bottleneck. Support operations on Hadoop by taking advantage of the Hadoop cluster by pushing down MapReduce jobs. Open and full integration with Office tools and third-party tools. So now I'm going to try, if I don't flub this, I'm going to try to do a very short demo. And I'm going to, since my, okay, I'm just going to minimize that thing. Let's see if this works. Having someone like me run a demo is always scary. So this is, I'm going to connect to a machine off someplace, single SQL 16 instance, talking to a 3-node Hadoop cluster, Hortonworks 2.0. Okay. Uh-oh. Now, what have I done wrong? Let me see if I drag this. Somehow I got from sharing screen into extending screen. But now I'm not going to be able to see the my laptop has some issues. So let me do this. Bear with me, I'm sorry. Display, mirror, project to second screen, duplicate. Oh, yes. Okay, so I have here, I'm going to start by, say, use this particular database. Okay. Now, for data, I have a data. This is the progressive example. I have an existing table in SQL Server called insured customers. Okay, the previous things are just some drops to clean up my scripts. So this insured customer has a customer key, has a geography key, a first name, a last name, marital status. So it's my insurance customers, and it already exists. So let me show you how easy it is to use this. So hopefully everybody can see that. First thing I'm going to do is create a file format. Okay, so this has to, again, as I mentioned earlier, this is part of imposing structure on that HDFS file. So here I'm doing a text file format. I'm calling FFT because the data happens to be in text out in Hadoop. It's delimited. The field terminator is this vertical bar, default type equal true. So I'm just going to simply execute this thing. And, oops, file format already exists. Okay, let's drop it so you can see you can actually drop these things. Okay, let me drop all these things just in case. Okay, didn't like that. So let me scroll down here. So here I'm going to, this time, hopefully successfully create this file format. So again, this is done once per file format. If you look over here in the Explorer, you can see we have this Poly database. It has a table. It has some external resources. It has file formats. All this stuff shows up in the Object Explorer as normal. And you'll see FF2, which I just created. There's also an ORC and RC1 that's already been created in this, for this database. Now, the second thing you need to use to use Polybase with SQL 16 is create one of these Hadoop clusters. So here I'm going to create one called HDP2. I'm going to give it a name. It's type Hadoop as opposed to Azure. The location is the IP address of the name node, and the job tracker is this resource locator. So you get a couple IP addresses, and again, you do this once per Hadoop cluster. Just once, and then you're all done. Never have to do it again. Hopefully that worked properly. And now, so I've got my file format. I've got my Hadoop cluster defined, and I'm going to create my external table. So it looks just like a normal create table command, except there's the external keyword in there. And there's sensor data and customer data. It's where I put my sensor data from my cars. It's got sensor key, customer key, geography key, speed, and year measured. And then it has these extra things. The location, what Hadoop cluster is on. That's the data source. The location is the file path. The data source is the Hadoop cluster. And then we have the file format, what to do with rechecks, et cetera. So I simply select this thing, and hopefully that works. So now I have a Polybase cluster, single node Polybase cluster, talking to a 3-node Hadoop cluster, and I've created a view, this external table, over the data in Hadoop. Now, let me just show you a few demo queries. So if I want to see the average speed from all my customers, I can run this query, and I can get the average speed of these, and it's not a very big, it's 18,000 rows, not a very big table. Average speed, and I'm sorry, I couldn't figure out how to zoom that thing in 45 miles an hour. Can you see that? You can see that okay? If I want to find out how many customers are people that I might want to turn their insurance off, so I'm collecting this sensor data in real time from the customers. I could have a trigger, and when I start to see bad behavior, I can notify the police or something. Call Quentin's wife. Okay, so here I've got 1,000 customers who have had sensor readings greater than 90 miles an hour. And again, standard T-SQL, data sitting in Hadoop. If I want the names of those customers, or I want more information, not just the count, yeah, that works fine too. And you see about 1,000 rows came back with the sensor ID, the customer key, the geography key. So far, that's kind of boring because all I've done is look at that HDF data. What I really want is the names of the customers. So I have a query that I have this relational table insured customers. I have this sensor data called car sensor. And I'm selecting the car sensor data for sensors that have gone more than 90 miles an hour, then done a join with this table in Hadoop with this my relational transactional customer data, and I'm going to run this thing. And again, it's going to take that speed predicate greater than 90, push it as a MapReduce job to the Hadoop cluster, run it in parallel on the Hadoop cluster, suck the results back into SQL 16, and do the join with the customer data. And hopefully this will work. So, and I'm going to get 1,005 rows back. I guess one customer has 2 sensors for some reason. I don't know what happened to those last 2 rows. So here are the customers and their average and the speed from their sensor. I could try a group by, but I'm not going to press my luck here. Okay, one more, and then I'm almost out of time. Sure. It depends how big your Hadoop cluster is. You're going, because Hadoop does nothing but table scans, you're going to scan all that data. One of the reasons I want to bring indexing to Polybase, and Polybase for SQL 16 and Polybase for the appliance, is that speed predicate greater than 90 can be indexed. So I can index my HDFS data in the same way I can index a relational table, and I can avoid pulling back any blocks of data from Hadoop or avoid processing any blocks of data from HDFS that don't have records where the sensor was greater than 90. It's the same. This isn't free text, so that's the difference between if we're if you're using free text search, maybe you could do it that way, using parallel query processing against the index. So anyway, so let me just run this one. This is one more, and then I'm going to quit. Here I'm going to actually do I'm going to select a bunch of customers. I'm going to pull them into fast customers. Then I can, once I pulled them in, I can create a clustered column index on top of them. And then I can, and this is fast customers. Oh, incorrect syntax. Oh, I have no idea. Artin set up this demo. Goodbye. What's that? Oh, pardon me? Oh, no, that's okay. I'm done. Okay. Very short demo. Hey, you get someone like me running a demo, you're always going to have problems. Great. Okay. So I want to acknowledge there are a lot of people that have contributed to this product. The entire Polybase development team, consisting of a bunch of people at my lab and a bunch of people in the SQL server organization in Alyssa Viejo and Redmond. So I'm just the lucky one that got to be able to talk about it today. Artin has been a PM for Polybase since the whole project started back in 11 and 12. He's just been an absolutely super PM, and I really appreciate all his help. He's the one that got me those good use cases for the customers, and he's the one responsible for the demo, and I really appreciate his work setting it up. Driver error is totally my fault. Okay? And finally, I want to thank you for coming. I hope this is of interest to you. My name is Dewitt, dewitt@microsoft.com. If you've got questions, comments, you're more than welcome to send me email. I read email all the time, so just dewitt@microsoft.com. And again, if you go to Gray, Gray, systems, SYSTEM, systemslab.com, you will oops, there's the URL. You can find these slides. You can find papers that we write because we're sort of a research group inside the product group. But you can find these slides. You can find out a lot more information about Polybase. There are a bunch of technical papers there. And Jim Gray, by the way, is a very famous computer scientist who was a Microsoft technical fellow, did a lot of early work on transactions and relational database systems. And my lab is named after him. You can read a little bit about Jim. So thank you very much for coming. I hope you enjoyed it.